Good morning everyone. Today we are going to find out the moment of inertia of this given cross section about x and y axis. So this is x and this is y axis. In previous case we find out the moment of inertia of given cross section about an axis passing through its centroid. So our job is first of all to locate the centroid, and then after we have to pass the two axes and we have to identify the moment of inertia of the given cross section about these axes. But right now this is case in which you have to find out the moment of inertia of this given cross section about x and y axis. So this is x and this is y. These both are not passing through its centroid. Right now the axis is here and y axis is here. So in this case, in this type of example, you don't have to find out the centroid. Even you don't have to locate the centroid and you have to pass the reference axis. You have to just take your section like this, and we are also following this step, discretizing this entire section into the basic known shape. So I am just here marking a reference line. Actually this is entire T section. I am marking this dash line here to divide this entire cross section into two non-basic shapes, 1 and 2. Both are rectangle. Alright, so this is 1 and this is 2. Entire section is a T section. This is a dash line only. Alright, and we have to identify the moment of inertia of this T section about x and y axis. This is x axis and this is the y axis. The dimensions are mentioned here. So as per your practicing in a tabulative format, the section 1 and section 2 you have to mention. If this section is divided in more sections, 1, 2, 3, then you have to mention the third row here. But right now we mention only 2 sections, so these are 2. Even we don't have to find out the moment of inertia of the given cross section about its centroidal axis, so there is no need to find out the centroid. So that's why no need to find out the x as well y. So I just mark this block here. But the area of the both section, that one is required. So as per this, as per we have this section, right? First and second, so both have the area. So this is you can say 100 mm by 10 mm. This is area of first section. It's a rectangle L by B. Right, so 100 into 10, so it's 1000. And for the second section is a 20 by 80, so 1600. Right, so 1000 and 1600. So we are going to mention the area of section 1. It's a 1000 and it's a mm square unit is mentioned here. And the second one has a 1600, 80 mm by 20 mm, so that's the 1600. And ax and ay, which one is also not required. So I just block this end, because we are in the practicing that we find out xy and area ax ay. So a into x, a into y. Alright, we are doing these practices, and then after we take summation ax, summation ay, as well as summation a. Alright, and then after we find out the x bar. This is coordinate of centroid. Alright, so summation ax divided by summation a, and y bar is equal to summation ay divided by summation a. But right now we don't have to find out moment of inertia of the given cross section about its centroidal axis, so there is no requirement to find out centroid. So these columns are not required to find. Right, directly we are going to calculate this ixx as well as iyy. And as we all know, this ixx and iyy have given cross section. So I mark it here, ixx for section 1 and iyy for section 1. For section 1, ixx is equal to bd cube by 12, and for iy1 is also, you have the equation db cube by 12. Right, so as per this given equations, basic equations that we discussed earlier in the first portion of introduction, bd cube by 12. So here b is equal to 100 mm 10 cube by 12, as well as the iyy of this given cross section is nothing but 10 into 100 cube divided by 12. Similarly, you can also find out ixx2 as well as iyy2. So ixx2 is a moment of inertia of the second section. It's a, so in this case this is a b and this is a d. So equation is remain same, bd cube by 12 and db cube by 12. So here for the first section b is a 20 and it's a 80 mm. So 20 into 80 cube divided by 12, and here you can say it's 80 into 20 cube divided by 12. So when you can also have this calculation of this ixx and iyy of both the section, first as well as second. So you can see these are the solutions of the ix and as iy. So as per this equation, if you solving this, these are the moment of inertia of these basic shapes about its centroidal axis. Alright. So this one is the centroid of section 1 and this one is the centroid of section 2. Right. So let mark the centroid of this section 1 as well as section 2. So these are the centroid of this rectangle and these are the centroid of this rectangle. And as we know, this centroid is located as a 80 by 2, means it's a 40 mm. So I can also mark this distance here. So you can have this value, it's a 40 mm. Alright. And the above side, alright, the total height, you can mark it here. The total distance of this centroid to the x-axis, which is from here to the reference line of centroid of this section 1. You can take the reference like this. Alright. So this is the distance. So it's a total 80 plus 10. It's a centroid, so it's a half. It's a 5. So you can say it's a 85 mm. It's a 80 and it's a centroid, so it's a half of this width. It's a 5. So total from centroid to x-axis is a 85. Right. Similarly, you can also find this centroidal offset as you can say it's a x bar. Right. So both these centroids are at the center. So I can also take the y bar of this both centroid. So first let me mark the first centroid here. The offset from y-axis for this centroid, right? If I take offset from y-axis, then it's a just 100 by 2 because this is the rectangle, whole length is 100 and this centroid is a half of the 100 mm, so it's a 50 mm. Alright, and the centroid of this section 2, I can also take this offset from y-axis of this centroid. So this offset, I can say it's also in the same alignment. Alright, both the offset have same alignment, so both have the same offset. You can take as a 50 mm. Alright, so this both offset as a 50 mm, as there's both centroid are aligned on the same axis, so offset will be same. Okay, so these are the moment of inertia. So this calculate all the moment of inertia we are going to drop down in the table. Right. So we have ixx, iyy of the both the section. So ixx of section 1 8333.33. So I'm going to mark it here. You can have this value 8333.33. And ixx of section 2 that we already calculated here. Ixx of section 2 is 85.33 into 10 to 4. So we are going to mark it here. 85.33 into 10 to 4. mm raised to 4 is the unit of this inertia. Similarly, we can have this iyy1 and iyy2. So for the first section, iyy is 83.33 into 10 to 4. So 83.33 into 10 to 4, and iyy of section 2 it's a 53,333.33. So we can mark it here. 53,333.33 mm raised to 4. Alright, this offset. So right now x dash and y dash, earlier we find out this x dash and y dash, so distance between centroid of shape to the centroid of the entire section. But right now we have find out the moment of inertia of this entire section about this x-axis and this y-axis. So we require this offset from the centroid to the reference axis. So centroid to the reference axis offset is a 50 mm, and for section to the center from the offset from y-axis is a 50 mm. Alright, and also we calculated this centroid to offset from x-axis is 40 mm, and this centroid of section 1 to the offset of x-axis is a 85 mm. So we have this x dash 1, x dash 2, as well as we have the y dash 1 and y dash 2. Alright, so y dash 1 is a 85 mm, as this is a y offset is a 85 mm for section 1, and this one is a 40 mm. Alright, so we are going to mark this all offset here as we already calculated it. So x dash in this both case offset x are 50 mm, right, for section 1 2, and y dash for section 1 is a 85 mm, and y dash for the section 2 is a 40 mm, right, that we already calculated. And what required ix and iy, and as we know this as per the equation of theorem of parallaxis, ix is equal to ixx plus a y dash square, and iy is equal to iyy plus a x dash square. All right, so here is a the column of ix. You can easily see it here. So let me just mark with this point. So it is an ix. Yes, exactly. It is an ix. All right, so ix is equal to ixx. So this one is ixx. So ixx plus a into y dash square. So in the first equation, for the first table, I am going to just make one example. So ixx of section 1, that is 8333.33, plus, you can mark it is a plus, alright, it is a plus, and plus area is 1000, as you can see the area is 1000. So ixx plus 1000 into y dash square. So y dash is 85 mm. Alright, so after solving this equation, you can have this ix value here. Similarly, you have to find out the ix2, like ixx2 plus a into y dash square. So area is 1600 and y dash square is 40 square. Alright, so you can solve this with the help of this theorem of parallaxes. You can put the value here. Similarly, for the y1, I am going to put one example. iy is equal to iyy. So it's iyy is 83.33 into 10 raised to 4 plus area is 1000 into area into 1000 into x dash square, correct? So you can also put a bracket here or multiply it directly, whatever that you want to present. X dash square, alright, so x dash, what is the x dash? X dash is a 50, alright, so you can take a 50 square. So having a solution, you can have this ix and iy value. So after solving this, you can have this ix1 is a 72.33 into 10 raised to 5, ix2 34.13 into 10 raised to 5, iy is equal to 33.33 into 10 raised to 5, and iy2 is a 40.53 into 10 raised to 5. Now you have to take the summation of this ix as well as you have to take the summation of iy. So if you take the summation of ix, then ix1 plus ix2 is equal to 72.33 into 10 to 5 plus 34.13 into 10 to 5, and this total is 106.46 into 10 to 5 mm raised to 4. And if you take this total of summation of iy values, then 33.33 into 10 to 5 plus 40.53 into 10 to 5, then summation of both this value is equal to 73.86 into 10 to 5 mm raised to 4. So these both are the moment of inertia of the given section, T section, about an axis x and y. So these both values ix and iy, we can say, is the moment of inertia of this T section about x axis and about y axis.